As you all well know, the first stage of the computational line stage, during the line stage, the task was provided by LHCb. And so the first section of today will be dedicated to LHCb, and our friends from LHCb came, and the section will consist of 3 parts. The first part will be a lecture by our friend from LHCb, Ricardo Gomez, and then there will be the second part by Nikita Kazeev, the creator of the task, who will tell you more about it, and then there will be the third part, where we will align 2 teams passed by 2 tracks on the line stage, and they will tell you more about their solutions. So I think that's enough for now. So I would like to invite Ricardo.
Don't clap yet. Talk can be shit. Okay. So thank you very much for having the opportunity of, so first of all for organizing this very interesting challenge that will help the research that we do at LHCb, and also for the opportunity of presenting you these challenges that we have for computer scientists in the particle physics world. So I'm assuming, so the idea behind this talk is that I'm assuming that you know half of the title of this, but you're not so familiar with the other half. So I will the majority of it will be trying to explain you what is particle physics and why we do particle physics and where we do particle physics. And the last part of the talk will be devoted to the problems that we have and the problems for computer scientists, and how we solve part of them, how the ideas that we have, your inputs, and the problems that we have. We haven't figured out everything yet. So, well, this is more or less what I said. So, let me start by the very last word here, which is physics. So, I went to Wikipedia, and I asked, what is physics? So, it comes from ancient Greek. Okay, so this is where we know what the basis of physics are, and it's the natural science that studies matter, its motion, and behavior through space and time, and that studies the related entities of the energy and force. And it's one of the most fundamental scientific disciplines, and its main goal is to understand how the universe behaves. So these are very, very, very high-level objectives, topics for physics. And, but I can agree 100% to what Wikipedia says, so there is no doubt about it. So understanding how the universe behaves. So this is a huge question, and this means that we want and we have to know the components of this universe at all of the scales, at the very large scales and at the very tiny scales. So this is physics. Now what is a particle? This is more complicated. Because it's something that changes with time. So if I were doing this talk in the 5th century before Christ, we would say, well, particles are 4, and these are earth, water, fire, and air. So these are the 4 elements of nature. And this is in ancient Greece, because my cultural heritage comes from the ancient Greek, but you can find similar lists in other cultures in the world. You can find the same things in Babylon, in Japan, in China, in India. And these were more or less the 4 fundamental things that were in nature, or that people thought that were in nature. But you can see that with this model, we have almost 0 predictive power. So the important things of physics is not knowing the things or how things behave, but also building up a model that allows you to explain things that will come into the future. So allow you to do predictions. And this is the important thing. So we started to do science at some point, and we discovered that there were other things. There were oxygen, there was nitrogen, there was phosphorus, and there's a lot of things that could not fit into this model. So when the experimental data does not fit your model, you do not try to change the data, you change the model. And this is how physics evolved. So all of these things could not fit. And then the scientific revolution
in Europe arrived, 1600s, 1700s, and a Russian guy that you know very well started to put all of these things into a very ordered way, which is the periodic table of elements. And this is something that you know from high school. They are not arranged at random here, they are arranged according to different properties that were observed of having these elements. So now as a physicist, I'm not happy of this, because I want the simplest model that I can. From simple things, I can build complexity. Because this is the difficult part. From very complicated things, it's super easy to build complicated stuff. The important thing is to have a very simple model with very few elements that is able to explain everything. So having all of these things is not making physicists happy. So just for curiosity, you will see now that we have fully completed all of this row. This is the 7th period of the periodic table. We have Moscovium here, because there's a lab close here in Dubna, where many of these transuranium elements have been synthesized artificially. So the last one, so these are named after Russian scientists, except for Technetium, that comes from Tennessee, because this was a Russian-American cooperation, which is also another important message of how we do science, is cooperation. But this complexity of all of these elements, even though there are many, could be explained after we discover the electron, and could be explained given the fundamental particles that are inside here. And I'm talking about neutrons, protons, and electrons, and how they interact together. So this gives the predictive power of expanding this table. This is not, we have fully completed this row, this final row, the 7th row, but nothing prevents having something extra here. And this is what we're looking for. We're looking for element 119, which doesn't have a name yet. And we can predict its properties. So this model, that it's based on other things, is able to predict heavier elements that have never been synthesized before. We have tried, but we are maybe at the edge of technology to do these things. So as I said before, this tells me that there are up to now 118 elements, but why there are so many? Why? Couldn't we find some more simple explanation of what is the fundamental block of, or what are the fundamental blocks of nature? And the answer is obviously yes, because this is what we look at particles today. So we have matter, and this is what we see. Matter is everything that is around us, that is made up of molecules and then atoms, and this is where the periodic table ends. Now we saw that the atom is not a full ball of something. It has a nucleus in the inside and electrons on the outside, wiggling around. And this is the part that atomic physics and nuclear physics studies. But then we discover that inside the nucleus we have protons and neutrons, and these protons and neutrons are not fundamental particles. They have internal constituents, and these are called quarks. And these live inside the proton and the neutron. And so far, as the science of the particle physics have come up, this is the fundamental building block. So these quarks are fundamental particles. And this is what particle physics, or we call them also high energy physics, studies. So fundamental particles are quarks and electrons, as we know today. This does not mean that in 20 years we discover that quarks are not fundamental. So does this thing sound familiar to you? To me, it looks like this. So we do not know which is the last matryoshka. We do not know if we have reached, if quarks are this or quarks are this. So the thing is that up to the knowledge that we have, up to the experiments that we have done, quarks are fundamental, but nothing tells us that this is a scale of 10 to the minus 19 meters, but nothing prevents that up to a scale of 10 to the minus 21 meters, quarks, we see an internal structure of quarks. Right? So, the model that particle physicists have today is we have our own version of a periodic table, and is this thing. So this is the periodic table of particle physics. Super elegant, only 4 constituents. We have 2 quarks, the up quark and the down quark. We are not very original in naming things. Sorry about that. So there were 2 of them, so up and down. And these are the ingredients of a proton. Proton is made up of 2 up quarks and 1 down quark, and also the neutron, which is made up of 1 up quark and 2 down quarks. Then we have the electrons, and also there's another particle that is not similar to the electron, but it's on the same. We put them on the same box of the electron because of reasons of particle physicists that are called neutrinos. Right? So these are the fundamental ingredients of all of the atoms that we have seen in the periodic table before, and of all of the atoms that will be created to fill the next row of the periodic table. And this is also the fundamental ingredients of everything that we see. Everything, I'm saying something that it's not entirely true, and you will see why in a moment, but the elements on stars, the elements on other planets, the elements on other galaxies are made up of these 3 things. Neutrinos are not components of matter. So I'm now super happy because I have 4 ingredients to explain everything. But no. Because with the years we did some other experiments, we went to probing different scales, and we saw actually that this column, this family of particles, there are 2 other copies. So there are 2 other copies, and these are called the second family and the third family, that are identical to the first one, with the only exception that the mass of these things is higher. Why we haven't discovered this before is because these particles from the second generation and from the third generation, we do not find them in nature now. They are unstable. This means that they decay. They disintegrate into particles of the first generation, always. So if you create, the only thing that we could do with them now is to create them on a lab. We create them artificially. But we observe that immediately after, they decay into something more stable, which is the particles of the first family. Right? And we have also antimatter, which antimatter is nothing to do bombs. It's something that exists, and it's something that is partly inside of your body because of decays, radioactive decays. You are radioactive. You know that? You are slightly radioactive. And there are certain, we had bananas outside. Who ate a banana? Okay. So you ate a tiny amount of potassium-40, which is a radioactive element. Nothing will happen to you, because we evolved in a world that contained bananas. So bananas had a tiny component which is radioactive, and this radioactivity that the bananas emit creates antimatter. Tiny amount, no, don't worry, you are not an antimatter factory. So this antimatter is exactly the same as matter. These we call particles of matter, all of these. The only thing is that they have the electric charge changed. So we know that the electron is negative, so there exists an antimatter particle that is like the electron, but with positive charge. And this is called the positron. Right? So with these, now yes, with these particles we can explain everything. The only thing is that there are 3 families. And this is a question, why 3 families? I was way happier with only 1 family, because this is the only thing that makes things. But there are 3 of them. And you are finding, for the first time in this talk, this particular particle that is called muon. And now you should know what a muon is, because you have spent 48 hours on dealing with muons. So a muon is a copy of an electron, a cousin, we say, with higher mass. There's another thing that is missing into this periodic table of particle physics, which is these particles are there, but they have to interact with each other. They have to speak. So the way that we see this interaction is through the exchange of other particles. And this is something that you're experiencing every single day as well. Because imagine that we are in a closed room, we switch off the lights, we remove the air, we give you some things so you can breathe, but so we cannot hear us, we cannot smell us, we cannot see us, and you are sit down. You do not know if you have someone sitting around you, because you cannot interact. So this interaction is, I can speak you, I'm sending you some waves. You would say, I'm sending you information. In the particle world, we say that I'm sending you some particles. So the interaction comes through these other type of particles. One of them you know, which is the photon. It's light. And this is the way of how these matter particles interact with each other, through the exchange of these other particles. So this means that light comes from the surface of your body into my eyes. If there is no light, I cannot see you. So if there is no light, you cannot interact with me, with the electromagnetic force. And there are other things, other particles, that are responsible for other forces. And then you have here the Higgs boson, which was a huge hit in 2012 all over the media. And this is the responsible of giving the mass to the other particles. So finally, this is the standard model of particle physics. This is our periodic table, and this is the name that it has. The standard model of particle physics. So all of this table put together, plus the antimatter particles. This is a triumph of human intellect. This is the most precise theory ever built, and the theory that gives the most accurate predictions ever. There are some measurements, there are some predictions from this model that have been tested, and they agree up to the 12th decimal point. This is an incredible amount of precision that this simplistic model, because in the end there are few ingredients, but this is really, really amazing. Actually, it should be called, not the standard model is super boring as a name. It should be called the amazing theory or something like this. So I've told you slightly about this, how particles interact. And as we know, they interact through forces. And there are 4 fundamental forces. You are super familiar with 2 of them. One is gravity. And you might think that this is the strongest one, and actually is the weakest one. But there is no anti-gravity, so gravity always adds together. But this is the weakest. Then there is the electromagnetic force, which is responsible of light, for example, and all of the things on the electromagnetic spectra, from gamma rays, X-rays, up to radio waves. This is exactly the same particle as light. And then there are 2 things that you might not be familiar with. One is the strong nuclear force, because have you ever wondered how the protons inside a nucleus can be tied together if negative charges and positive charges repel, so positive and positive repel each other? This is what we learned at school, and this is electromagnetism. So how come protons with the same electrical charge can be inside the nucleus. This is due to the strong, it has to be stronger than the electromagnetic. Nuclear, because it acts at the nucleus force. So there is some other charge, which we call the strong nuclear charge, that allows that protons are tied together into the nucleus of the atom. And there is one other force which is even weirder, which is this weak nuclear force, which is responsible of the radioactivity that you get when you ate the banana. You say, boy, this is not so important. The sun works thanks to the weak nuclear force. So if it wasn't for the weak nuclear force, we would not be here. So the particles that I showed you before, plus these forces, is how we explain nature today. But as I said, this is up to the current knowledge. This does not mean that in 20 years from now, in 100 years from now, the picture would change. So how we do to look at these particles? So here what I show you is this scale of the universe. You have from the super tiny, which are these quarks, up to the radius of the observable universe. And you can imagine that we need different tools to see different things. So if you are at the scale of 1 meter, which is more or less now, which is more or less us, with the eye is more than enough. But then if you want to look at bigger things that are farther away, you need telescopes or radio telescopes. If you want to see even larger scales and larger structures, you could need these gravitational waves interferometer, that are something that is also came hot last year, these gravitational waves. Oops, sorry. If you want to look at the tiny, you start with microscopes, but certainly these particles have not been seen through microscopes, because the microscope uses light, and light is actually bigger than these particles, so you cannot see them. So the way that we use is using particle accelerators and then a particle detector to see these particles that we create in the accelerator. So, and this brings me to something that is very linked, which is these two sides of the picture are super linked. Because we see some structures and something weird going on at these scales, at the very large scales, that has to be explained with this standard model of particle physics, but so far is not. And one of them is dark matter. So dark matter is, this is an observation from the early 19th century, sorry, from the early 20th century. So the thing is that we observe that the galaxies, you know that galaxies rotate, because everything rotates in space. And you can measure the amount of matter that there is. You can ask your personal astrophysicist and say, measure the light, the amount of light, and then the amount of matter that this galaxy has. Okay, they measure this, and then you measure how fast they rotate. And this rotation depends on how a particular star is closest to the center of the galaxy or farther away to the center of the galaxy. No? And this is what you measure. These points is the measurement. Then you take your Newtonian physics, which is something that everyone knows, and you see, okay, if I have the mass and I have measured the rotation velocity, this is my expectation. And you see that it's way off. So, what's the problem here? To the best knowledge that we have, there is missing mass. And this missing mass is not of the form of the mass that we know, of the mass of the other particles. It's something that we do not know, and this is why we call it dark matter. Here is something more fancy, but it's the same phenomenon, so it's the same explanation. So this is the Ballet cluster. So these are two clusters of galaxies that have come together, and they have collided. And there are many interesting phenomena observed. So when two stars pass by, they interact very, very few. We are colliding now, our galaxy is colliding with another galaxy, and you do not feel rains of asteroids or anything. So when two galaxies collide, essentially nothing happens. And this is what is depicted in this pink things. But then there is another interesting phenomena, which is behind the picture. You see the stars that are in the background and the galaxies that are in the background. And Mr. Einstein told us that when you have some mass and some light from behind, when this light comes, it bends. So this is a phenomenon which is called gravitational lensing, because the mass acts like a lens in your glasses. So it deflects the rays of light. So you create some patterns that you can compute the mass that this pattern, which is the mass that created these patterns. And this is what you see in this blue. So essentially, all of the mass is in the blue areas, but the things that we see is only in the pink areas. So there is a difference from the matter that we see and the matter that we know there is there because of this gravitational lensing. So this is, if this is some sort of particle, and it has to be because it behaves like a particle, it should be included into this model, and it isn't. So we know a few things about this. It has mass because we observe this effect and this effect. It does not emit light because there are no stars of this thing. It interacts very, very weakly, so it's not, because if it had a strong interaction, we would have seen already it. And it also moves slowly. So these are the few things that we know. But we don't have a better explanation or a better solution of what this dark matter is. And we are searching for it. And this was the easy thing. Because then there is something even more strange, which is dark energy. So this also comes from observation. Everything in physics has to come from observation. And we observe that the universe is expanding. So this is something that we know. Then it arrived the Hubble telescope, 1998. And it measured the expansion of the universe in galaxies which are far, far away. And then compare it to galaxies that are closer. So when you look at farther objects, you are looking far away in time. So what the Hubble telescope saw was that this acceleration, this expansion of the universe, was expanding at a lower rate before, so for galaxies far away, than the expansion that we measure now. So it means that the expansion is actually accelerating. And this is more or less depicted here. So this is the slope of the slope is of the contrary, but okay, you get the idea. So this thing is working against gravity, because gravity tries to pull everything together, but there is something that is trying to pushing everything farther away. And this is what we call dark energy, and we know nothing else about this. We don't have any other hypothesis, but without this dark energy, all of the other observations that we make in the universe do not make sense. And we can compute the amount of matter, and we can introduce these in the simulation models that the astrophysicists have. And if you do not account for dark matter, and if you do not account for dark energy, you cannot predict what we observe now. So these things have to be there somewhere. Some of them we have few candidates, for some of them we don't. And this is dark energy. So how much is it? It's a lot. So this is the matter that we know. 5%. The table that I showed you before is 5% of the content of the universe. There's a factor of 5 of dark matter beyond this, what we call ordinary matter. And this discrepancy is what makes these curves not matching. And there is 70% almost of something that makes the universe expanding in an accelerated way, which is dark energy. So this amazing model of particle physics, this standard model that is the most beautiful theory, the most accurate theory ever, is only able to explain 5% of the universe that we observe. Because this, I repeat, this is based on observations. So it's not that good, this model. It's extremely precise in what it does, but it's not complete. It does not mean that it's wrong, because what the standard model has explained, you cannot unexplain. So it has to be incomplete. There is something, some corner of the universe that this model is not able to account for. So, but this has to be enclosed into a bigger theory, if you wish. So do we know everything? Of course not, because of all of these things that I've told you, but also gravity into this model does not fit. There is no particle for gravity. There is a particle for gravity, but these particles, the quarks and the electrons and the muons, are essentially not affected by gravity, and we don't have a way of including gravity into the standard model yet. This is a problem, a current problem of theoretical physics. There is no way of putting together gravity, special relativity, and quantum mechanics. We do not know what is dark matter, what is dark energy. There are other problems that these neutrinos have some mass, but we do not know where this mass comes from. We have the Higgs explanation, but the Higgs is not responsible of the mass of the neutrinos. This antimatter thing, it should be also here. We should see more antimatter than what we see, so we do not know where it went. We do not, this is more philosophical, but if you wish, it's also a problem with, that I told you before, with the complexity. Why there are 4 forces? Why couldn't I explain everything with one force, and this force, electromagnetism, is one single force, is not the electric force and the magnetic force, is one single representation of this. So can this thing put together into a bigger framework? The answer is yes. The electromagnetic force and the weak force we have already seen that is the same version of the same mechanism. So could this be expanded into the other forces? We do not know yet. And why there are 3 generations of particles? Why not only 1? Or if it's 3, why 3 and not 31? There is no 4th family, as far as we know. But the evidence, data suggests strongly that there is only 3 families. So why 3? So everything would be very easier if there would be only 1. So these are all of the problems, and there are few other problems that this model have, but none of the experimental results that we have measured since the last 60 years show any discrepancy with the prediction of the model. So it's the best incomplete model that we have ever come up with. So how do we test this model? So this is how do we look at the universe. So here we had the Big Bang, and this is not to scale, but this is where we are today with galaxies, stars, and planets and things. But what you cannot see because of this is a very bad contrast. But you see here time and also energy. So if you were to see these numbers, you would see that the energy that we have now as the universe the energy is conserved, but the volume is high. So the energy, the density energy, if you wish, here is lower than it was here, and is lower than it was here, and lower than it was here, and so forth, so on. And this is why particle physics is called high energy physics. Because if we want to study what happened here, we have to look at how the universe looked when it was few instants after the creation of the universe, after the start, if you wish, of the universe, how these particles behave, and they behave at very high energies. This is why we call it high energy physics. So, you see here that this region, so up to here we can observe with telescopes, but here we need accelerators, particle smashers, if you wish. Because this is, so we built today two types of things, telescopes and radio telescopes, and particle accelerators to look at different stages of the universe. So one of these particle accelerators and one of these facilities, and this is the place I work, is CERN, which is in near Geneva, and is the largest laboratory in the world, and it's host to the Large Hadron Collider. I'll explain you a little bit after. So the Large Hadron Collider is this yellow ring. It has 27 kilometer in perimeter, and you see here, so this is Lake Geneva or Lake Le Mans if you're French or Swiss. This white stripe here, this is the Geneva's airport. So you see more or less the scale of this, and you see, well, here this is the Mont Blanc. And what you see is also these different things. So these are 4 experiments that are in the accelerator. So I will tell you a bit the difference between the experiment, what is an accelerator and what is a detector. So these are the experiments. And you see that this is crossing 6 times the frontier between Switzerland and France. So this line represents the frontier. And this is relevant also for you as an audience, because this is where the web was born. So www was a protocol developed at CERN to interchange information between us. We were not interested in Facebook or something. We were interested in exchanging information between physicists, because the only way at that time was I print my program and I go to you, and there was a courier service at CERN providing these things. So I will give you my program, and then so this was very inefficient. So Tim Berners-Lee said, I have this protocol. Internet was not invented at CERN, but the web was. So www, and this is why it's free, because it was developed at CERN. So this is more or less how this LHC, this Large Hadron Collider, looks like. So people working at the accelerator has to move into somewhere, because you cannot reach 27 kilometers easily. So this is the tunnel. It's a tunnel which is built 100 meters underneath the surface, more or less. It has 27 kilometers, as I said, and this is how it looked like. So these are magnets, essentially, that move particles around. So it's the coldest place that we know in the universe, except if there is an alien civilization doing some sort of particle physics experiment. But it's at 1.7 Kelvin. So the universe on itself, we can measure the radiation and we can measure the temperature, and it's at 2.3 Kelvin. So this is even colder than outer space, as you would say. And it's host of 4 giant experiments. So, tiny history of CERN, just one slide. It was founded in 1954, so right after, more or less at the end of World War II, where European science was not longer first class. Everyone went to the United States. So there was the brilliant idea of some physicists of creating a lab that would put all of the European forces together. We were enemies 5 years before. But collaborating in a peaceful way would bring back the center of nuclear facilities to Europe. Because nuclear facilities were very interesting at the time. They were very expensive, but by putting many countries together, it would dump the cost of them. So this is very relevant for what CERN became after. And this is an extract of the council constitution, if you wish, and it says that the organization shall provide collaboration, first thing, among European states in nuclear research for a pure scientific and fundamental character, and in research essentially related thereto. The organization shall have no concern with work for military requirements, and the results of the experimental and theoretical work shall be published or otherwise made generally available. This is why you don't have to pay each time that you do www, but you have to pay for an internet connection, because this is www was made generally available. So they were geniuses in establishing this picture, which was not easy. Look at the time, where a peaceful, non-military nuclear facility was built. And now today, this is more or less the distribution of what CERN looks like. This is the most updated figure that I could find, but it's only 24th of January of last year. And there are 23 member states now of CERN, with more than 13,000 scientists all over the world. This is the countries in different colors that have at least one CERN user. And also it's important that CERN is an observer at the United Nations Council. It is the first and the only one so far scientific organization that works as an observer of the United Nations. So now, moving on to more details. So the 4 big experiments. So we have these particles which are protons that we accelerate into this tube, and they travel different paths. They travel 2 separated paths. One is clockwise, and the other one is counterclockwise. And we made them collide. We made them meet together into 4 different points. And in these 4 different points, we built a huge photocamera, but we call it a particle detector. And these are the 4 detectors or experiments, we also call them, that are at the Large Hadron Collider. And these are ATLAS, CMS, ALICE, and LHCb. And this is another, you already know LHCb. So these are big, and this is a person, this thing here. So ATLAS, for example, is 40 meters wide across and 21 meters tall. It's like a building of 7 floors. This is CMS, and another picture, and these are ALICE with another human being here, and LHCb, which we do not have human beings, but is more or less the same size of ALICE. LHCb is something like 20 meters long. So they are not big, they are huge. So what is an experiment? An experiment is a scientific collaboration, and we are more or less 1,300 members from across the world. It's a particle detector, so it's a huge photocamera, and a huge photocamera means of the order of 100 megapixels. That is taking 40 million pictures per second. So it's taking a lot of information. So this is also interesting to you, how we deal with this information. It has an extreme resolution. So even if it's 20 meters long, the resolution that we have in Spain is half of the thickness of a human hair. So it's extremely precise. And it's entirely automatized. So there is no human intervention beyond checking that everything works. And also it works like an enormous filter, because everything of these 40 million pictures that we take every second, not everything is interesting for us. Not everything will give us dark matter particles or things that we do not know. Because the things that we are interested in are super rare. So it means that they happen very, very, very rarely. So there is the probability of creating a thing that is interesting is not that much. So we have to select everything. We cannot store 40 million pictures per second for 10 years or for 20 years. So we have to filter them somehow. And it's also composed by many different layers. It's not one single piece of material that does all of the things, but it measures different things. So how we do detect particles? So it's like the particle experiment is like an onion. So it has different layers. And for example, here, this is a section of this cylinder. So the collision happened here, and particles move to the outside. So the first thing that we want to know is where particles passed, and this is called tracking, and it's at the very internal layer. Then we have huge magnets to measure the particle momentum. Then we have something called calorimeters to measure the energy, and here we destroy the particle. We make them collide with something of lead or iron or something very dense. And then we have the muon system, another ring to you, which is at the very end, because muons have this property of traversing everything essentially without being changed. So you could say that the only thing, or at first order, the only thing that arrives to the later edge of the detector is a muon. But you see that putting all of this information together, we can pinpoint which type of particle is there. So we know the shape of the muon in the detector, we know the shape of the photon in the detector, the proton, the neutron, and the electron. And only these ones, because these are the only ones that are stable within the detector. The rest decay immediately. So they decay here. with the exception of 2 that were your background in your studies. But essentially, these are the only particles that we see in the detector. So putting together all of this information, we can reconstruct what happened here. And this is another keyword, reconstruction. So the LHCb experiment in itself, this is the same picture as before. We want to answer one of the questions that I put you before, which is, where is the antimatter? So we are interested in seeing the differences between matter and antimatter. So we have to create antimatter, we have to study this, and then we have to do the same thing with matter and compare. And this is the main purpose of the LHCb detector. So you see also here that it has, with a different shape, but it has the same parts, essentially. So we have the interaction point here at the beginning, then we have some tracking, then we have the magnet, calorimeters, and muon system. So it's exactly the same thing as in another particle detector, is that the shape is arranged differently because of reasons. And this is another thing that you are familiar with now, which is the muon system of LHCb. So you now know that it's at the very end, and it's built specifically to detect muons. So how do we, this is super bad contrast. So we want to measure something this is an example only, but we want to measure things that I told you before are rare, so they happen not very often. And I'm taking this case, so it's a particle that it's called Bs, so you can imagine that it's made up of a quark called B and a quark called S. I told you before that we're not very good with naming. That decays, so it disintegrates after some time into 2 muons. So this is why your objective was to study these 2 track muon things. So this is very interesting, this because of the implication that observing this decay will have, but it's very, very rare. It only happens 3 times in every billion that one of these particles is created, right? So you see here one of the events of LHCb. This is a real event. You cannot see anything, but there were few white lines here. So this is where the interaction happened. So at the interaction point, you create this Bs, and this Bs does not decay immediately, but is able to live some time, very tiny amount of fraction, so it allows the Bs to travel, on average, 1 centimeter. And then at this point, it decays into 2 muons, which are these magenta lines. So the idea of this picture was that there were some white lines here, but few of them. And you could say, okay, so this is very easy because I see these 2 things. I can make brute force, I make all of the combinations, and I just find the right one. The problem is that nature is not that kind with us, and it's not only 10 particles here, but everything looks more like this. So there are thousands of particles per event. Per every time that we have this collision, and we have 40 million per second, there are thousands of things. And only 2 of them, maybe 3 times per billion, will be one of these Bs to mu case. So I'm showing you the data volumes that we have to digest. And this is also, so I'm starting more or less discussing the challenges that we have for computer scientists, if you wish. So we have these 40 million collisions per second. In each collision there is roughly between 10 and 100 megabytes of information. 1 in every 10 billion, I wrote here, produces one of these interesting decays. So you can imagine that if we were only interested in this, we cannot keep everything and then filter out. We have to make real-time decisions on this filtering. And this essentially tells us that we can record up to 10 kilohertz. So only 10,000 per second, we store them forever. The rest are thrown away forever, and we will never know what were there. So this decision, and this is what we call trigger, has to be first fast. So we have to read the detector fast, before the next collision, so this is every 25 milliseconds. And we have to make a decision of keeping the event or throwing it away. So that more or less, so this is a complicated thing, and this is one of the crucial parts. This trigger thing. Yes, okay. I will rush. Sorry. So the data throughput of LHCb is only 10 gigabytes per second, but the typical year is 5 million seconds, and we have been running since 2011. I leave you the math to you. So another thing that is important is how to filter this thing, because so this is the result of the analysis of LHCb of this BS mu. So the BS is this red huge peak. So you see that this is very evident. So it is something standing on top of the rest, right? So there is no clear that this thing is here. But this is after several stages of analysis, because at the very end, at the very beginning, sorry, everything looks like here. So the scale here is arbitrary, but you see that there are thousands of events. Here there are tens. So we have to discriminate everything. We have to remove everything, and this has to be done somehow. Usually now is machine learning techniques. Is multivariate things. And if you go and look at the papers of LHCb, you will see that essentially all of them use some sort of machine learning, multivariate things. And this is where most of the work comes from. So into designing the multivariate algorithm or whatever, and to training it properly, because I don't want to lose my signal. I want also to be robust. It's not that I want it to be trained on tiny fluctuations. I want it to be something that is that scales properly. And I told you about signal, but signal, we don't have one signal. There are many of signals. There are many different things that we're interested in. There are thousands, actually. So there is not one signal and the rest is background, so the tuning everything at the same time is a very complicated problem. Because each of these signals has its own type of background, has its own type of things that appear here and that you want to remove. So optimizing everything at the same time is not that easy. And also because your signal can be my background, and my signal can be your background. So there is no one-to-one correspondence between signal and background. So you see here, for example, 2 examples. This is one signal for one study that we did, and there are more or less 10 candidates. On the same data, another type of signal, which is different, contains more than 100 million. So you see that the differences in scales that we have to deal with are very different. So one single object and optimizing all of these things is not that easy. Also, there are things related to simulation, because we want to understand the response of our detector, how our signal look like, how our background look like, but in a controlled way. So we have to simulate real life, and then we have to study it. But the simulation has to be as precise as the real detector. This means that every single cable has to be depicted properly into the simulation. It's not that I have a monoblock of something and then I don't know what happened next. And also the simulation has to be fast, and this is the next paradigm that we are tackling now, because I do not want to study 100 million of signal events with 10,000 of simulation. I want to have more or less the same amount of simulation that I want that I have as in data. So we want as many simulation as data, and we want so many that essentially 90% of our computing resources are devoted into creating this simulation. And this is what it's telling you in this green blob. So the green and also this pink is things that are simulation. So everything, 90% of the resources go into simulation. So this is what the simulation does essentially, but you see that the most important thing is this, the simulating the passage of the particles to the detector, which is very costly in terms of resources, computational resources. And some of the solutions are or parametric simulations, or machine learning simulation, or other fancy stuff. So one thing that we do is to do, instead of simulating everything, we do some parametric things, and this is something that is being developing now. And this is using neural networks instead of simulating every single interaction with the material. So we train a neural network, and of course using the real data as an input, and you see that more or less the distributions agree. So the field one is the real full simulation, if you wish, so the slow one, and the histogram, so the line, is this parametric thing. So you see we have two pieces here that we want to separate, so the separation is done properly, and also one overlaps with the other. So this parametric simulation seemed to work very well. But as always, the devil is in details, because I not only want to train this, so to generate this fast, I also want to preserve correlations, because you know better than me that multivariate object will learn from the correlation. So if I kill the correlation using this, then I will be screwed in my later stage. Also, another things that we do, that these you know better than me, these are these generative adversarial networks that are used to reduce the details into the simulation. Because there are many things that are very detailed in the simulation, but then the detector reconstruction is coarser. So why do I have to spend some time into generating every single tiny detail if then I will see, yeah, 35. It does not matter. So there is a test, and if you want one thing, you can ask Nikita, because he's one of the authors of these things, that you generate similar objects to the reality, and then you try to discriminate them. You try to discriminate, well, you know how this works, the real from the fake ones. No? And you stop when this discriminator does not see any other difference. So these are two examples, for example. So this is a real I mean full simulation, and this one of these generated with this thing. So to my eyes, they look exactly the same. So this is also very, very promising. But again, also the problem is within the correlations of these things. That this is something that different problems that we have to tackle in the future. Oh, sorry. And just a few words. I'm less than 4 minutes. So this is not the end. We are planning for upgrades. We are planning for upgrades of the detector, and we are planning for upgrades of the accelerator. That will allow us to take 5 times more data, or 5 times faster the data that we took it now, and this is what you see with this slope. So we are here. The slope from 2021 to 2024 will be higher, and then from 2031 on will be even higher. So, because from here we want to take data 50 times faster. Because as I told you before, the things that we want are very rare, so we want to create more of them. So, well, this is a quote from Alice through the Looking Glass, but essentially she said that, well, we are running so fast, but in my country, running fast means that I get to go somewhere. And the Queen said, well, this is a very slow country. You have to run as fast as you can to be in the same place. But if you want to be beyond, you have to run faster. You have to run twice as fast at least. What do I mean with this? That all of the problems that we have, creating more simulation, dealing with more data throughput, these sort of things, if we do nothing, we will be swamped. So we have to run faster to be at the same place, at the same amount of data that we can handle now. So we have to develop new types of algorithms for the reconstruction, and for the simulation, and for everything. So this is more or less the throughput. I'm only interested in that you see the output. So this is, well, 5.6. I told you 10 gigabytes per second before. In 2021, they will become 40, and in 2031, they will become 400. So we have to deal with all of this data, and also the readout of the detector. We have to chew this information before we can spit it out. These will pass from 4 terabytes per second, more or less, to 40, and then to 500. So we are exploring also alternatives to do this thing faster and better and in a stronger way. We are studying using GPUs instead of normal CPUs. But as I told you, this is still work in progress, and as I told you, you have to multiply all of the things, all of the problems that we have before by a factor of 10 or by a factor of 100 in rates, complexity, everything. So now, this is very, very last part. Why you had to study 2 muons? Because this is up to now, so yeah, muons are there, but why? Why they were important? So muons appear in more or less half of the analysis that LHCb has done. And this is because they are very interesting outcome of the decays, but they are also very relatively easy to select and to reconstruct. But many analysis relies on the purity of its muons. I do not care if I have 1 muon and another 100 particles that look like a muon. I want that the purity of having a muon is very high. So I want a low probability of the muon to be misidentified, we say, so we mistake some other particle with a muon. And I told you before about the BS2 mu. So this thing we recently discovered in 2017. But we started looking, not LHCb, but particle physics in general, start to look at it in 1985. And this was the quest. So this is the measured abundance of this. So now we know that it's 3 times in a billion. This is this line, this blue line. But at the very beginning, with fewer data, we said, okay, so this is smaller than 1 time in 10,000. So this was the quest for searching for it. Up to, and this is an inset, up to in 2014 more or less, and now 17, we definitely observe this decay after more than 30 years of searching for it. So this is also a lengthy process. And we are close to the discovery of a relative to this BS, so this is called a BD, so you can imagine B quark and D quark, the down quark. So this is the same properties, but it's even more rare. So it's 1 time in 10 billion, not in 3 times in 9 billion. And this is this thing here, this green thing. So the red one is the well-established thing that we discovered. And this green is this BD, which is extremely interesting, but is not discovered yet, and it's very rare. And the problem, and this is why you had to study 2 muons, is you see this magenta thing. This is background. And the only source of this thing being here, so it has the same mass, it has more or less the same shape, and is at the same place. So I can barely distinguish them. And the only reason why this magenta thing is here is particles that I think there are muons, but they are not. So having a more powerful discriminator of 2 tracks that are muons can help us in reducing this magenta peak. Because it's only by reducing this, I cannot push this data upwards. The only thing that I can do is push down this contamination. Right? So I'm done. So in the many years of particle physics, it has always been a source of problems to you, or challenges if you wish. And also this, in the future, with the upgrades that we are planning and the things that we are developing, they are not going to disappear. They are going to stay, obviously. So our relationship, particle physicist and computer scientist, our interaction have to be strengthened, if you wish. But also we have a problem, that is we cannot follow what the industry does, because we have a restricted budget and we have restricted resources. And as you can imagine that the problems that we have in a private company, they would say, okay, you just buy more computers and then you would solve everything. But we cannot do that. We have different constraints. So we need custom tools, we need hybrid solutions, we need to work this thing together to solve our specific problems. But it's always fun, and I wouldn't have a job if there weren't interesting problems to solve. And thank you, and sorry for taking too long.
Can you touch the dark matter? Can you lift
touch?
it? Yeah.
No, because it's...
So when you mean touch, you mean hold it in your hand. The thing is that it's so weakly interact. To hold something in your hand means that, so, okay. Blowing your mind a little bit. Essentially, atoms are void. So the mass is on the center, but the electron is moving around at a distance of, if the atom, if the nucleus were on the center of a football field, the electron would be on the goals, right? So in between there is nothing, there is vacuum, there is void. So to touch something means that these two electrons have to be in touch with, so in equilibrium more or less with each other. The thing is that as dark matter does not interact in this way, electromagnetically, it can pass through. So you cannot hold it. It has some weight because it has mass, and this is what we see, but you cannot, it does not interact in the way that, so here you say, I'm holding this. No, are the electrons in my hand and the electrons in the paper repelling each other and floating around. With dark matter, as they do not interact in this way, this does not happen. It's the same thing with neutrinos. So neutrinos do not interact electromagnetically, so we cannot hold neutrinos. You are traversed by neutrinos every day, by billions of them, so, and you cannot hold them. Sorry.
So where does string theory fit in this model?
Okay. So string theory should have its name changed because it's not a theory. So let me explain. This is the difference between hypothesis and theory, which is not relevant for linguists, but is very relevant for particle physics and for science in general. Einstein had a theory, Darwin had a theory, Newton had a theory. I don't have theories, I have hypotheses. A hypothesis is something that you make up, you've made some observation, and you make up something to explain this. If this is then confirmed by data and you can predict something, then you have built a theory. So it's a step further, a hypothesis. You have confirmed the hypothesis. The problem with string theory, so string theory tries to explain all of this standard model of particles as one single thing, that is this string, and everything that we saw are different representations of this string, if you wish. But string theory so far, so mathematically it's beautiful, it's very elegant, because it explains a lot of things. But it hasn't done a prediction yet, so we cannot test it. So I can only test your theories if you predict something, or if you compute something and you say, okay, the mass of something with my model has to be this number, even if it's not something that is new, but you have to explain the things that we already know. String theory so far is not able to do this thing. So this is where string theory comes, but it's not a theory yet. It's a string model or string hypothesis.
So it is one level deeper.
It's deeper. It's deeper in the sense that it can explain these 3 families of quarks. It can explain gravity into this thing, adding some other features. For example, 11 dimensions instead of 4, which is, but okay, this is not a problem. But yeah, it would be a higher level explanation of what we observe. But it still is not able to predict anything.
Thanks.
Could I just propose, since we exceeding our timeline, in half an hour we have a coffee break, maybe we will continue in more unofficial manner this communication. Don't you mind? Yes, sorry.
No, sorry for taking...
No, you gave a perfect lecture. I mean, that was interesting for me, the international collaboration guy, but let's give it up to Ricardo. Thanks a lot. And again, in half an hour we are to have a coffee break. So Ricardo will be here as well as Nikita. So please come and ask the questions about the sphere. And
you can have your question.
what's up?
You can have your question.
Thanks for the presentation. It was brilliant. So you said at some time in past we found out that there's this family of particles, right? The first family. And then you said later on we found out that there are other two families. And then you said in physics everything comes from observation. And then you said, but these two families are not observed in nature. So to an uninformed like me, it sounded like a contradiction to elaborate.
Okay, I wasn't clear. When I say they are not found in nature, I see when you look and to stars, when you look to Earth, when you look to materials. This is what I mean, they are not found naturally, so in a natural way in Earth. This is the same thing as this Moscovium element. This is not found on Earth. This is created in a lab, artificially, if you wish, but we have to create them, and then we can observe them. So the same thing happened with these other two families. They do not occur here, but if we do an experiment, we create them. So this is, yeah, I wasn't clear of what do I mean by they are not found in nature. It's not that they do not exist. It's that they existed in the past at the very early stages of the universe, and then they decay. And we cannot find them around us anymore. But they were there in the past. Right?
Thanks again. And I would like to introduce again the creator of the task for line stage, Nikita Kazeev. And yeah, let's greet him. I'm giving the stage.
Thank you. It's a pleasure to see you all in person. Well, I hope that my task would be more technical, but at the same time more interesting, because this is actually about the problem which you all have faced, and I'd like to discuss as one of the possible solutions. Now about the negative weights, or the S weights as I call them. I'll just begin explanation with a simple, silly toy problem. I have a data set which would have kangaroos and cats. And then we asked some people to label this data set. And some of those people were drunk. And a drunk person has a much higher error probability than a sober person. And then we know that for each labeled image, what was the condition of the assessor who was labeling that image. Then for simplicity we say that as we had the same number of kangaroos, the same number of cats, the same number of sober and drunk assessors. And now we want to answer some questions about the data set. So with the kind of labeling we have, can we accurately measure the number of legs a cat has? Or can we prove that there are no two-legged cats? Because of course in our data we will have cats labeled as kangaroos. And since we're dealing with weights, we want to solve our problem in the fashion of the weights. So if we knew the ground truth labels, then we could just compute the average number of legs by computing the average over the ground truth cat images. Now we don't have ground truth, and we want to invent some source of weight. So then we sum over the whole data set with those weights. We would arrive at the same number of legs that we want the cat truly has. And here we come to the first observation, that if we restrict our weights to be non-negative, we cannot solve this problem. Because as soon as a single kangaroo says meow and is labeled as a cat, we will have our average biased. It doesn't matter that all other cats are labeled with some other weights. If soon as a single kangaroo has a positive weight, we no longer have a correct average. Now, the moment we relax the requirement of the weights being non-negative, we are able to solve this problem. We can find weights which provide us that a number of legs on a cat is 4, a number of legs on a kangaroo is 2. Well, that was a simple still problem. Now we go more formally and more generally. And we have data set which has been populated by the data from different sources. And for each example, we don't know from which source it comes from. However, there is a special feature, M, and we know the distribution of this feature M for all the sources of the data that we have. And we know to reconstruct the distribution of some other feature X, which is independent from M. Reconstruct it for one particular source. So we want to find such weights so that when we weight our data set with them, the distribution of feature X would be the same as if we had only a single source. Now, this is how it looks in high energy physics, that we have our masses, and we have a signal source, we have background source, and then we have some variable which can be a loss of a classifier on a given example. So we can, nothing prevents us from using this machine learning formalism. Now I will not bug you with math. If you would like, there is a paper which has been advertised. In general, the curious thing is that the transformation is linear, but otherwise that's it. Now, of course, if we are as advertised, if I apply the S weights, I would reconstruct the distribution. And what now I say, fine, that's fine, I have my weights. Now I want to do machine learning. And I take a neural network and I try to fit it on the data set where some examples have negative weights, and here you observe a learning curve. And I think most of you have already guessed why it happened, because as soon as you have a data example which has a negative weight, it means that if the algorithm is able to isolate it, that it can bring its loss down to the minus infinity while ignoring the rest of the data set. Or just single example and as small loss as you want. Can we do something to prevent it? It appears that yes, we can. Imagine that we knew everything about our data set. We knew all the distributions. That we knew distributions of M, we knew distributions of X. Then we, of course, could construct, instead of the S weights, we could construct normal, ordinary weights, which would be the ratio of the probability density functions. And now, second observation is that using the S weights, on average, results in the same distribution. So if you weight X with this, and if you weight X with S weights, the distribution of X would be the same. So here is what we propose, that the average S weight for examples with given features equals to its probability of being signal. Of course, there is a catch here that in your data set you had like 60 dimensions and some variable length arrays. We cannot just go and compute average S weight conditioned on features. And here is when machine learning comes to rescue. That that if we fit a regression on some data which doesn't have one-to-one correspondence between features and the result, the regression would converge to the average, the same average that we want to find. And the algorithm which we propose is twofold. So first, we fit a regression that averages the S weights for us. And then we use the output of this regression as a sample weight to the classifier which would solve our classification problem, which we started from. Of course, here you can use some sort of cross-validation. Sometimes it brings better results, sometimes it doesn't. And one last thing is that we know that the probability of a given example being signal is a probability. It lies in the interval of 0-1. And in practice, it makes sense for better results if we restrict the regression output to 0-1, put a softmax on it. Now let us return to your IDAO case. Well, we had a setup which was built like from elementary particles Ricardo told you about. It was built from several S-weighted data sets. We had 3 kind of particles, and for each particle we had what we call pure particles, and we had a corresponding background. So something which we want to reject, and we really had 6 sources of data. And we wanted to know, to build a binary classifier which would separate one muons from the 2 others, while ignoring, while don't care how our classifier behaves on the background examples. And to help us with removing the background, we had the S-weights. So they separate from muons, pions, and protons. It's pointless to compare S-weight from muon to S-weight for protons. They were obtained by different distributions and different fits. And we also, to make things more complicated, we not only had the S-weight, we also had some kinematic weight, which we provided you helpfully as a separate component to enable you to do tricks like here. So when we evaluated the methods which I am describing, we fitted a separate regression for each particle type and its corresponding background. And here is the results table. What we tried here is, okay, I was lazy, I just took 500 trees, so I didn't want to wait too long. Then I trained, of course I have access to all the trained test data, so I trained on train, I validated on public test, and then here are the scores from the private test, and have 4 possible ways of handling the S-weights. And as you see, if you just include them as weight, CutBoost still converges, because CutBoost is a tree-based model, and it actually splits your data in bins, so it cannot really isolate a single negative weight example to diverge the training. But still, you having as example weight negative violates all sorts of guarantees which are provided by machine learning algorithms. We observe that the scoring as a result is worse. So then one could simply ignore the S-weights. Again, the viability of this tactic is obviously dependent on the problem and the data set. Here, the results even better than using them directly, mostly because we have relatively pure data with a relatively few amount of background, and we didn't have a situation where muonic background looks like pions. Then one of the strategies which some of you used in your submissions was to take the absolute value. Again, it provides a jump in quality, because the S-weights, the absolute value of the S-weights also carries some meaning, that in some regions we have fewer data points and it should count. And if you use the approach which I just introduced, this provides, again, a small increase in the predictive power. Increase is small in terms of absolute values, but since it's a competition, I think it would be interesting to hear about it. Now, I don't want to detain you from the coffee break and stuff. So, to conclude, the S-weight is a way to precisely account for a certain kind of label noise from machine learning point of view. Physicists are not interested in label noise and stuff like that. They're interested in just reconstructing the distribution X. Very interesting to learning on such data. So for us, it's a label noise. And then now you know a way to deal with it in a rigorous fashion. So if you ever participate in a machine learning competition designed by physicists, I hope this knowledge will be useful for you. And also there is a code on GitHub been sitting there since autumn, which implements regression bounded to 0, 1. So, thank you very much for your attention. Now I'll be glad to answer any questions you might have about the S-weights and maybe about the first round of the IDAO in general.
Okay, first of all, isn't regression constrained to 0, 1 as a classification? I mean, classification predicts probability from 0 to 1.
I think it's a question of terminology, like classification and regression live in the world of loss functions. So you can, I mean, you can fit a machine. You can say you can get XGBoost regressor with the mean squared error, fit it on the data with zeros and ones, and will it be a regression or a classification? I don't know. I call it a regression because we use the mean squared error here. So, and we actively want so from point of view of this thing, it is doing a regression, and we know that the result is a probability, but this thing thinks that it's doing a regression.
So it's basically classification with different loss. Instead of log loss, you use mean squared error.
In principle, we use this, and yes, and then observe that we use a special property of the S-weight. That here we don't use label. We don't use we don't use label. We just use the S-weight. It's indeed as simple as it sounds. So I was disappointed when it wasn't discovered in the top solutions which I viewed. So yes, here we just do we use this property of the S-weights to do this classification without having negative example weight and with this regression loss function.
Okay, so the second question is about the. Could you give a comment about the ground truth, which is unknown? So you had the slide second to the last with this one. Not conclusion, but before that. So as far as I get, here you kind of test out whether S-weights help the classification, right? Because like introducing S-weights and regression improves the score, but how do we know the score? We don't have ground truth. If we just calculate on the mixture, isn't this score?
Is it use the same thing which you used in computation? I use the S-weights. So here I just use the S-weights to compute the rejection 90% efficiency.
So you test whether we should or not use S-weights.
No, I say different ways to use the S-weights in training. I say, okay, we will use the S-weights in validation because that's the only thing we can do. If we don't have ground truth, this is real data from real collider, and we don't know. But what we can do, we can use the S-weights, and these numbers, there is no better way. I don't know no better way to obtain them. The question here is that what can we do during the training? Can we avoid? Can we avoid these traps of infinite negative loss? And how, in practice, it improves our quality.
But why can't we use a synthetic problem where we know the ground truth?
I did. It's just, it's in different talk on a different conference. So here I just restricted myself to the data set which you had available. Of course, you can do the same exercise for synthetic data. And depending on how you produce your data, you will have different numbers. Obviously, those numbers are property of the data set. Now, there is a gentleman on the back, because 3 questions for you and 0 for him so far.
Thank you very much. So, I just have one question. It still has a problem when, for example, we try to predict and we predict correctly the class 0, the little class, the small class, and we predict correctly, we still have negative weight in the scoring function in the final, right? So it doesn't help us to deal with this problem when we predict correctly all 0 classes, but some of them have negative weights in scoring, in general scoring, and then we have our score reduced.
It is a misunderstanding of how the S-weights work. The idea is that if you produce the absolutely correct classification, then you would still have the optimal score. Then what you would like to do is say if you could find the negative weight example and separate it from the positive weight example, which is near it, then it would break all the formalism, and the idea is that it is impossible because of the requirement of independence. I think, yes, here. We say that in reality, like not in reality, in terms of mathematical distributions, if you look at a certain feature set, and then you will not have a single, and you have a distribution of examples which this feature set, then you have to label all of them at the same time, and and what would count only not to say some of them are negative S weight, some of them are positive S weight, only the average will count, and the average is always non-negative. In this sense, this is not a problem because true labeling will always be optimal. Oh yes, and then one of the purposes why we had this competition was to see whether machine learning can hack the S weights. Because if we can do like you say, if we could find negative examples and then somehow do some sort of trickery, we want to know about it because this is physically incorrect. But, and we want to find if it's possible, how should we amend our data analysis methods. So, is there more further questions? Do we have time to call the teams?
Yeah, we have around 10 minutes before the coffee break. So now we would like to invite two heroes teams of the online stage. The first one that took first place in terms of score in first score, which is, sorry if it's pronounced incorrectly, TR, or or
how do you pronounce it yourself?
Yeah, that's why
we'd like to know.
Yeah, that's why we're actually bringing you here to clarify the pronunciation. Yeah, and the second team is Improve Y. I guess Y is for Yandex. You wanted to improve your chances by putting Y. Yeah. So please come in. If you just could give any overview on your solution, how you did it, and maybe some interesting particularities and features.
Yeah, sure. Because we made not a class classification for protons, ions, and something else. They all are charged particles that should deflect a magnetic field. So our main features was something based on mass and velocity vectors, and differences between velocity vectors across different sections of the accelerator. It's I can say about each meter. And there is a lot of peculiarities in the data set. Instead of fitting regression on weights, we just zeroed negative weights, and it provided great boost in the sense of metric. And also we observed that for some reason, if you took, for example, the first half of training data set, it will improve your metric as on the rest, or as if you compute your metric on the second half, if you do the test, or or on the public dataset. Also, if you take the first half, for example, and make duplicates twice, it will also boost your metric on the public training test. I don't know why, because it seems like you're overfitting for something, but in the description of the dataset, it was told that the data was taken from the real accelerator, so it can't be happening. I'm very interested why it is happening. Yeah, that's all.
Could you please elaborate didn't quite get what is the setup in which you have overfitting?
Well, basically, you have very big train set.
Correct?
And you just take the first half.
Yes.
And you just duplicate it.
Yes.
And then train and validate on this duplicated data set. Of course, you're overfit on the validation.
Mm-hmm.
And take this classifier, average over some classifiers, and make prediction on the test.
Mm-hmm.
And your prediction of the test will be better if you will train on the whole train data set without duplications, without duplicates.
Yes, my prediction of the train, the data will be better if I train on the whole.
That's right.
Isn't it what you would expect? That if I train on the whole, my predictions are better?
That's right. The solution was provided, but it's a very interesting peculiarity. I couldn't repeat it.
If you train it on the whole dataset, you're saying if you train it on the whole dataset, it's worse.
I have a proposal for you. Namely, our public test data set is small. I mean, it's really small. So if you're comparing two scores on the public test, what is the difference statistically significant?
But also it would provide better solution for the local test. So you basically take the first half as your train, yes, and the second half as your test,
yes,
and your score will be also better for the local test.
That's funny because the data should have been shuffled. It has been shuffled. Okay, thank you.
And sorry, I haven't mentioned that Improve Y was the best team according to the second try. Sorry. Yeah, please.
Hi all. Thank you for the IDAO for that competition. So our solution was consist of two parts. First one was consist of generating a lot of features. Features were firstly it was some feature from the study about which is related to closest hits and something like that. There was something like determining variable from the study. The second, we generated features which were consist some features with velocities, angles from the extrapolated points, and something different between matched hits and extrapolate and something like that. The third one is actually I forgot about that features. We changed negative weights to minimum of positive weights. It was have some big improvements on the cross-validated set. And as the models, we have two models, CatBoost and XGBoost. And it was very fun that we have big improvements on the validation because they trained on the different schemes. CatBoost has depth approximately 8 or 7, and XGBoost has head weight 5. And they have different schemes, and it was ensemble of this was have very big improvement on the validation. And also it was very fun because it will be very easy to overfit because our validation model was very bad on the public leaderboard, and we chose that, and it was height is a private leaderboard, and it was very related to the validation score. It was thank you.
May I ask about the second track? So I was mostly interested in what did you have to sacrifice to fit into the time and memory limit?
No, we haven't got this. Our track was without time limit, isn't it? No, there is another track, I suppose. Our track was without time limit, so we have got a lot of models there.
Well, okay, so we have to ask the third. You ask.
No, we are improvising.
Okay. May I ask then the
TR.
yes, what did you do to fit into the time and memory limit? Sergey, who won the second track then?
The first track was about the best solution.
Yes.
And the second one's about the best solution. So this
Yes.
that's the best solution.
Okay, and who thinks he won the second track?
Second track was without time limit.
With time limit.
With time limit. So your team, no?